All right, so let's talk first about increasing, decreasing, and constant functions. So we say that a function is increasing on an interval. So let's take a look at the words here. It says, if and only if, for any 2 points, a positive change in x results in a positive change in f of x. Which means, if I go from x1 to x2, right? F of x, so from x1 to x2, I go in the positive direction. And f of x1 goes in the positive directions to f of x2, right? So in going from one point to the other, the y value goes up or increases. That's an increasing function, okay? A decreasing function here, a decreasing function is the opposite. And so that says a function is decreasing if when you go from x1 to x2, when you move right on the x-axis, the respective y values will decrease. All right? And then a constant function is if when you move from one value to the right to another value, if you go from x1 to x2, the y values will stay constant. That's a constant function. Back in the day, when we learned linear functions and you had positive slope, we called it increasing. It rises, it falls, and so on, right? Well, here it increases or decreases because we're talking about not only linear functions, all right? Okay, so one thing students always miss is when you're reading a graph, it's like English. You go from left to right, not like Hebrew, right? So you always start at the left and you go to the right when you're reading a function. So from here to here, is the function decreasing, increasing, or is it constant? All right? So let's write that up here. Always read, and read in quotation because you're reading a function, graphs left to right. Okay. So take a look at this function. Consider the following graph to determine the intervals on which the function is increasing, decreasing, or constant. So you want the intervals on which the function is increasing or decreasing. Intervals means you want the x values over which the function is increasing, decreasing, or constant. All right? Okay, so like I said, there is an arrow here going down to the left, right? But when we read functions, we go from left to right. So take a look at this one. Starting at the left, this function is increasing right until here, and then it starts to decrease, right? So this function is increasing right until here, and then it starts to decrease. So here it's increasing, and then here at that point it starts to decrease, and then it's decreasing until here. All right? And then it's increasing again until right there. Then it's constant. Okay, so the way we're going to do it is we're going to figure out where the function is increasing, decreasing, and where it's constant. All right, so first the function is increasing from negative infinity all the way to x equals -3. Only the x values. So from negative infinity to -3. And then where else is it increasing? From what to what? 2 to 6. Good. And that's it. And where is it decreasing? From negative 3 to 2. Okay, I'll talk about that for a minute. And then where is it constant? From 6 to infinity. Okay. Okay. So there is a theorem in calculus that says you can have these basically either as parentheses or brackets, right? So either will work. So you can do this, or you could also, put them in brackets like this. The only thing that can never be in brackets are at the infinities. Okay?
Doesn't the 6 have to be though?
No. No. Because at the 6 there is another function as well. So all of them can either be in like this or like this.
What are the functions?
And okay. All right. Look at this one, and it says use the graph to estimate the intervals where your function is increasing, decreasing, and so on. Okay, so look at this function, right? It's very clear, as you're going up from the bottom here, that it's increasing, and then we get to this point, and students are always like, okay, there's a little area there where it's constant, right? But if you think about it, what is the function for that? It's 2x cubed. Are there any cases where you can put in consecutive x values, like increasing x values, and the y value will stay constant? Does that ever happen? No. For every x value you put in, you're going to get an increasing y value. So if it was, let's say, 0, 0.01, 0.02, 0.03, when you cube each and every single one, your y value is always going to increase. So this function is increasing from negative infinity to infinity. Okay? All right. Let's take a look at this one. Look, it's decreasing until this point, and then it starts to increase. So we say decreasing from negative infinity to 2. I'm going to close it. And then it increases from 2 to infinity. It decreases from negative infinity to 2.
Just to clarify, the 2 did not have to be that.
Right. I think it's easier to bracket than not. Okay, it's easier to put a bracket than not. Okay, so here, all right, where is it? It's increasing from where to where? Negative infinity to 0. And then where is it? And then it's increasing again from 3 to infinity. And then where is it decreasing? None, right? Okay, so if I had a space for it, increasing, and then decreasing, go ahead and write none. But if it's up to you to write them, then you don't have to write it. You don't have to include it. Right, on homework you wouldn't have to. And it's constant from 0 to 3. Okay, here. It's yeah.
Wait, so why is it increasing from 6? Why isn't it from like 6? Isn't it from 6?
It's the x values only. Always x values. Wait, the increasing?
Yeah.
So look, it's constant until x equals 3. And then starting at x equals 3, it starts to increase. Okay, so this next one, it's increasing from negative infinity to what? Negative 1. And then again, 1 to infinity. And then it's decreasing from negative 1 to 1. Okay, now we talked about increasing and decreasing. All right. Now, this leads us to what we call maximum or minimum. All right, so let's stay on this example here, D. Look at this. It's increasing until here. Why can't I write? It's increasing until there. And then right at that point, this starts to decrease. Right? So at this point, the function changes from increasing to decreasing, right? So it was going up and now it turns around and goes down. Now, it's pretty much common sense that when something is going up and then you turn it around and go down, you're going to make a little mountaintop over there, right? You're going to make a little hill. Is that right? Now, in the other region, look, it's decreasing and then it switches to increasing, right? And when something switches from decreasing to increasing, you make not a mountaintop, but a valley, right? Yes? Those happen to be critical points on a function in math. We call points like that extrema, extreme points, right? So take a look here for a minute. We're going to talk about relative and absolute extrema. All right. A relative maximum of a function is the greatest value that it can attain in a certain interval. So look at this. Every time you have a peak like this, that is called a relative maximum. All right? So each of those are a relative maximum in the vicinity of that region. So when you're at around x equals a, this is a relative maximum. At around x equals b, this is a relative maximum. All right? It's called a maximum because it's the top of a mountain. If you go down here, the valley are called relative minimum. All right? So maximum, minimum. Okay? Now, how do you get a maximum? You get a maximum when a graph changes from increasing to decreasing. How do you get a minimum? When it's the opposite. It goes from decreasing to increasing. Okay? Now, when you're in the region of when that happens, each of them is called a relative maximum. Now, the absolute maximum is the highest point that the graph will reach in its entire lifetime. Okay? So, in the model on top, is there an absolute maximum? Yeah, this is an absolute maximum. All right? The rest will just be a relative maximum. In the one on the bottom, is there an absolute minimum? This is an absolute minimum. It is the lowest point the graph will ever reach in its lifetime. Okay? Yep. 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 Now, one thing I would like to specify is some notation. So first of all, when we hear the word extrema, that refers to minimum or maximum. All right? Now, if you're asked, where does a minimum or a maximum occur, you give the x value. When you're asked what is the minimum or maximum value, value always means y coordinate. Cool? Where is x? What value is y? Okay? Okay. Let's take a look at this. So estimate and classify the local and absolute extrema on the graph of this. And so I've graphed this for you, right? Are there any, Are there any maxima here? Let's do maximum. Are there any maxima? Yes.
The relative maximum at x equals 3. I mean, x equals 0.
X equals 0. So here, that's a maximum, right? That's a maximum at x equals 0. The way we write it is, you say 0, 3, or we say f of 0 is equal to 3. If I ask you for the coordinate points, give me that. If I ask you in function notation, give me this. Now, this is not an absolute maximum because the graph actually goes higher, right? We don't know what the highest value it achieves is because it's infinity, and we don't know what infinity is. So that we're going to say is a relative maximum. Yeah.
So, what would be the answer?
Relative maximum at 0, 3.
Okay, so you don't just say the x value.
Right. Here. Relative maximum 0, 3. Okay? All right. Minimum. There is a minimum here and here, right? These are minima. Because it's sharing the minimum value, again, we call it a relative minimum. So we're going to say relative min at -1, -1, and what? 1, -1. Okay?
Or do you have to put negatives
I do. Huh? Okay, here we go. What do we think? What do we got here? Absolute minimum. It was a relative because it was 2 that was being shared. No, we just say relative. That one is like more convention than anything else. It's relative.
But like if it like said absolute, you just write.
Yeah. I mean, it'll usually say like what are the extrema. So there is an absolute minimum at -3, -4. So again, the location of this is x equals -3, and the value is y equals -4, right? Make sure you make that distinction. Okay, here we go. Yep, waiting. Yes. No, just the first one. This I'm just letting you guys. For function notation, it'll be f of -3 equals -4. Okay, let's do function notation for this one. Okay, so let's do the maxima first. Where is there a maximum? Here, here. That's it. So in the directions, right? Support your answers numerically, use a calculator, right? So if we're given a calculator, we're going to figure out like the exact values of these, like the decimal equivalents of them. So look at the first one. It's on a corner, so it's -1, 2, right? So I say, okay, is there an absolute max here? No. So I say relative max at what? So it's f of -1 equals 2. Okay, the other one, we're going to do it with our calculators. I'm going to come back to it. Let's do some minima. There is a minimum here and here. Again, they're relative min. And one is f of 0 equals 0. And then there is another one, right? So what I want you guys to do right now is I want all of you to graph this function on your calculators. Okay? Now, here, this side of the room, I want you to find the other maximum. That side of the room, I want you to find the other minimum. And then you're going to let me know. Correct. So this one is f of 0.659 is equal to 0.478. Okay? All right. Evan, did you find the other minimum here?
Yeah.
Okay, tell me.
F of 1.9 equals -4.19.
Correct. All right? Question? No? Oh, I thought you had a question. Yes. Sorry.
So, let's say like,
Let me see. So I was saying if you go into,
I created a new document.
okay. All right, so let's do this next one. Let's do this next one. We're going to plug in this calculator. I'm sorry, we're going to plug this into the calculator. Approximate to the nearest hundredth the relative or absolute extrema for each function. All right, so go ahead and plug this one in. Now, in the real world, in calculus even, we don't really say relative min, relative max. Like we know it's a relative min or max. We don't write it though. So we'll just say max and then absolute max. Okay?
Which way do you want us to do this one?
Yeah. So we're going to write it in function notation. So we're graphing -x cubed minus x squared. Right. Or it'll be something that you should know how to graph, like a parabola.
Yeah.
Yeah.
Oh, because then you a parabola.
Mm-hmm. So
it'll never just be like that, though.
Right. Correct. Yeah, something like this would be on the calculator section. So here we go. I'll remind you one last time how to find these points, right? So we're going to do menu, analyze graph, minimum, right? I want to find the minimum first. And the minimum is here. Again, for lower bound, if your minimum is that point, the dashed line has to start for lower bound to the left of the point, a smaller x value, the lower x value. And then here, you already see it, it's -1.22, -3.11. So, yeah.
I don't know if you explained this before, but what would happen if you put the lower bound on the right?
There will be some functions where it'll either give you an error or the wrong point, or because the way, okay, so that's the thing, see, the way the calculator finds it is by increasing and decreasing. To look for a minimum, it looks for where the functions are decreasing, and then where they start to then increase, right? And if you give it to him in another order, then they will not know, okay? So, So this is a minimum, right? Not an absolute minimum. And it's f of negative 1.22 equals negative 3.11. Then it's up to you. You're free. You have complete and utter freedom if it's not specified. So the other one, menu, analyze graph maximum. And again, lower bound, upper bound. And so now as you drag it, see it's looking that the values are increasing. And then the minute they start to drop, it says, okay, that's where the maximum was, right? So that's it right there. 0.55 and negative 0.37. Equals. All right. I don't think I need to do the other one. I think you guys get the idea, right? Yeah. Okay. Let's move on to bigger and better things. All right. So here, optimization. Interestingly, optimization is what I'm teaching in AP Calculus at this very moment. I just finished teaching optimization in AP Calculus, and now I'm teaching it to you guys. So, and the fact that you get to see it 2 years in a row means it's pretty darn important. So we're going to get you used to the concept now this year, and then we're going to do it using calculus next year. Okay, optimization is an area of mathematics where one is looking for a maximum or a minimum quantity given a set of conditions. So for example, you have to construct a cup out of this material that can hold 10 fluid ounces, right? But you have to use the least amount of cardboard possible, right? In order to maximize cost or maximize profit, right? So that's an optimization problem, okay? You guys do it all the time. Like, what's the minimum I can get on this test to end with the highest possible grade at the end of the semester? You guys do optimization problems like all day long, especially like in December. Okay, so take a look at this one. Advertisements for a new car claim that a tank of gas will take a driver and 3 passengers about 360 miles. After researching on the internet, you find the function for miles per tank of gas for the car is that cute little function. What type of function is that? It's a parabola. It's a quadratic function which gives you a parabola. Where x is the speed of the car in miles per hour. What speed optimizes the distance of the car on a tank of gas? How far will the car travel at the optimum speed? We just read and passed by a lot of information and none of it stayed in my head. So now I'm going to go back and now I'm going to highlight, underline, square, and so on. Put in a square, all the things that are important. So first of all, advertisement for a new car claimed that a tank of gas will take a driver and 3 passengers. Here we go. About 360 miles. That's important information. That is distance. Okay? After researching on the internet, you find that the function for miles per tank of gas is this. Okay? So what this is miles per tank of gas. Now, x is the speed of the car in miles per hour. Now, here's what you're looking for. What speed optimizes the distance the car can travel on a tank of gas? All right? So let's define our variables and all that good stuff. My independent variable is x. X is the speed in miles. Okay, my dependent variable is f of x. F of x is what? It's the distance per tank. And it's in miles per hour. Sorry, this is miles per hour. I'm sorry. I did that wrong. This is miles per hour and this is miles. Okay? Yeah. No. So the advertisement says you could go for 360 miles, but then you find that that actually depends on the speed that you're driving, right?
Oh,
Okay. So the advertisement says you can go about 360 miles, and then you do some research and you go, you know what? That actually depends on how fast you're driving. So now you go, okay, what speed should I drive at so that per tank of gas I can drive the most distance? All right. So what we need here, what do we need? This is what we have. What do we need? We need the maximum distance, right? We need the maximum distance that this car can travel. And what is the maximum speed that you should go at for that to happen? So what we're going to do is we're going to graph that function. Okay, so now we have a function. We're going to graph it. It's negative 0.025 x squared plus 3.5x plus 240. Okay, I don't see anything. Why? Because, okay, so what does x stand for? X is the what? The speed, right? What's a good range for speed? A car goes from what to what? So menu, analyze, window settings. So we're gonna go from 0 to, you know what? 100. Okay, so the car could actually like go a possible of 120 and so on, right? But okay, so 100 is it, because what if you could go above, like what if you could drive above 60? So think about what's a realistic speed to drive at. 60 is not the maximum speed that we drive at, right? We're being realistic, okay? Okay, so let's go to 100. No one's gonna go above 100 when they're driving. Okay, y is the distance that you can go on a tank of gas. So it's gonna go from 0 to, the people estimate 360. Why don't we go a little bit more? And why don't we go to 400? Let's splurge. All right. So you should see a maximum here.
Wait, mine looks
So the maximum speed would be 0.
That's like she put in the same equation.
All right, so that's what it is, right? After fixing that equation here. So you see that like here I had this as a times. That's why it was giving me the wrong function to start with. All right, so this is now the distance that it could travel per tank of gas, right? Based on the speed. So if you're going at this speed, you know, this is how far you can travel. If you're going at this speed, this is how far you can travel, right? So think about it, like miles per gallon, you have city miles per gallon and highway miles per gallon, right? The highway miles per gallon are always higher, right? Because you're not doing like the stop and start. Okay, so we need to find the maximum here. Let's go to menu, analyze graph, maximum. I'm not sure exactly where the maximum is because it's such a flat curve. So I just take a wider range and let the calculator calculate it for me. And look at that. It's 70 and 363. So, yes. So maximum occurs at 70, 363. Now remember, this is x and f of x. So the first value stands for the x and the second value stands for f of x. All right, so it says what speed optimizes the car can travel? That's 70 degrees. When you're going at 70 degrees, the car travels the greatest distance. 70 miles an hour. Sorry, I haven't done a trick for so long. Okay, so optimum speed is 70 miles per hour, right? At this speed, the car can travel a maximum distance of 363 miles. So, if a question like this shows up on the test, and it will, the thing is, you need to know, are you looking for a maximum or a minimum? You need to know what is the appropriate window for you to get a reasonable graph, okay? A lot of them, yeah, for max, min, yeah, a lot of them, yes. Matthew. Okay. Average rate of change. The average rate of change between any 2 points on a graph is the slope of the line through those points. Okay, so suppose this was, again, the same situation. This is the distance that a car can travel on a tank of gas based on the speed, right? And if the speed is, x1, it can travel that distance. And if the speed is x2, it could travel that distance. So if you're driving at 50 miles an hour, that's how far you would go. If you're driving at 90 miles an hour, that's how fast you would go. What's the average? How do you find the average? You draw a line from one point to the other, and you find the slope of that line. Okay? So when you draw a line between the 2 points, you have a line, just like in algebra 1, and now you have 2 points on a line. And if you had 2 points, would you be able to find the slope between 2 points? You were able to find the slope of those points years ago. All right? So, okay, in geometry you learned that when you have a circle and when a line touches the circle at one point, what's it called? A tangent. And then you also learned that when you have a line that hits the circle at 2 points, what's it called? A secant line. What we're doing here for the average value, for the average rate of change, when you draw a line that hits the graph at 2 points, it's called a secant line. And when you find the slope of that line, you find the slope of the secant line. Okay? Back in the day, we taught you m was y2 minus y1 over x2 minus x1. Now, what's the new y? F of x. So now it's f of x2 minus f of x1 over x2 minus x1. We're not going to let that phase us, right? y2, f of x2, same thing. Okay. Students see this problem on a test and they blank out. They're like, oh my God, I didn't know what to do. I think the reason why it happens is it's such a straightforward concept. Nobody spends time studying it the day before the test. Don't let that happen to you, okay? When you see average rate of change, you have to find the slope between the 2 points. So that's what we're going to do here. We are going to find the average rate of change this is the slope of the secant line. And it's f of x2 minus f of x1 over x2 minus x1. Okay, you're given the interval -3, -1. Those are your x1 and x2. So this is really f of -1 minus f of -3 over -3 minus -1. Right? -1 minus -3. Ooh. Okay. Now, how do I find f of -1? What do? I plug it into the function, right? So here, let's work here. F of -1 is -2 times -1 squared plus 4 times -1. Who's really quick? Who can get that for me? 0. Minus, what's f of -3? -2 times 9 plus 4. -24. Over 2. This is 24 over 2. 12. Okay?
So is that the secant slope?
That's the slope of the secant line. Okay, in the next case, it's even easier, right? I have 2, 4. That's the interval, and I've given you the graph. So this is x equals 2. This is f of 2. And this is f of 4. So the slope of the secant line is f of 4 minus f of 2 over 4 minus 2. What's f of 4 these days? -2. Minus +2 over 2. That's 0, right? Is it? Yes? No. No. Yes. Good. -4 over, just checking. -2. All right, so that's the average rate of change. Okay. One lockdown and you guys are so trusting all of a sudden. All right, so this homework is due Wednesday.
How do you write that interval?
Yeah, so it would be that the average rate of change is 2, a -2. So this is going to be due Wednesday. Yeah.